Let's consider the photoelectric effect. This was one of the experiments that was being performed around the year 1900 that led Max Planck and Albert Einstein to propose the quantum model of light. In the photoelectric effect, light strikes the surface of a material. Depending on the material and the frequency of light, electrons can be ejected from the surface. With the appropriate electronics, the electrons can be collected and a photocurrent can be measured. Each material has a minimum or threshold energy required to knock the electrons off the surface. Thus, light was viewed as a form of energy. As an example, it might be that for our surface, violet light would have an energy greater than the threshold and be sufficient to eject electrons, whereas lower energy orange light would be below the threshold and would not produce photocurrent. If the light were a continuous wave, energy would build up at the atoms on the surface. If we had a lamp that shined violet light, which in our example is of sufficient energy, we could imagine the energy building up until it was greater than the threshold energy. That would result in an ejection of an electron. If an orange lamp were used, which is of lower frequency and lower energy, less energy would build up. The problem with this continuous wave picture is, of course, that if you simply shine the light longer, it would eventually build up until the energy was greater than the threshold. The observation is that shining the light longer does not produce any photocurrent. In other words, for our hypothetical material, shining the light longer does not result in an electron being removed from the surface. Likewise, using a brighter orange lamp, which in the wave model is represented by a wave with a larger amplitude, also does not result in an electron being removed from the surface. Brightness does not affect the energy that the surface atoms can absorb. Planck and Einstein explained this inconsistency by modeling light not as a continuous wave, but rather as a flux of photons. A single photon interacts with a single atom on the surface. That photon either does or does not have enough energy to eject an electron from the surface atom. In the case of violet light, the energy is above the threshold. In fact, if we use the appropriate electronics to collect the ejected electron, we would find that the extra energy above the threshold is related to the kinetic energy of the electron. Again, orange light is less energetic. When an orange photon interacts with an atom on the surface, less energy is absorbed. Rather than ejecting an electron, the surface releases this energy in a different way, usually through heat. The next photon can again interact with the surface, but this is a new event. Again, the energy is below the threshold. We see these photon interactions as individual events. Unlike in the continuous wave model, energy does not build up. While a single photon interacting with a single atom may be an oversimplification, the interaction of light with the surface is seen as a series of individual quantized events. A single photon either does or does not have sufficient energy. We say that light is quantized in photons.